So I pasted some links in the Twitch chat, but they're just these links that I have up here. And they're just like some reference material for lean tactics that we might look at. And today we're going to try to prove some very simple things about lists, because with the regular expressions, like which is the big project we want to prove things about, list proofs come up a lot because strings are just lists. So we need quite a big library of very basic proofs on lists. And we're going to start building up this library today. Lean already has quite a big library, and that's found on this link I'm highlighting with lemos.lean. But we also have previously proved a lot of things in Coq about lists. So we'll also see if like we can port some of these over, because it's like it was the start of a bigger tactic we created called Listerine, because we like to have funny names for our tactics. And yeah, this is just the basics, but we want to build up to a tactic that can simplify or prove a lot of things for us about lists, so that we don't have to think about it, because it gets really annoying really quickly. So it's worth putting in this foundational work.
Yeah, and then maybe a stretch goal for today or in the future is to figure out how to integrate these lemmas with the proof automation in Lean. You can add them to like a simplification database, or maybe we need to write tactics. That's like an open question.
Yeah.
But so it'd be nice to see that, how that integrates with the automation.
Yeah.
You don't want to have to apply these lemmas about lists. It's nice to have them, but you don't want to have to apply them directly. You just want to, like in Coq, we would just use the tactic Listerine, and it would apply all its knowledge about lists onto our goal and onto our assumptions, and just to simplify the proof. So we didn't even have to think about what lemmas about lists we were using.
Yeah.
So,
for example, in this case, like if you know, here's like a very simple proof about a list that just has one element, at least one element, right? So L could be empty, but we know there's at least one element in the list because it's const with a list that can be anything. So we know that cannot be equal to the empty list, but we really don't want to think about that ever. We just want to say, yeah, obviously this isn't true, and we just want to continue with our lives. But there's hundreds of these, so you really don't want to even remember their names.
No,
you just want to say, yeah, this is an obvious listing, please do something, or at least take me forward. Like, yeah, split the list up. Maybe there are certain cases for this where that is kind of obvious, but yeah, we'll see. So where do you want to start? Like maybe
maybe prove a few things about lists.
Yeah,
we've already done something here.
Yeah. So this is a simple one. We can just restart just for.
Yes.
Okay. So in this case, we just want to say, like, yeah, if you const something to the start of the listing, that cannot be equal to the empty list. So there's probably a better way to prove this, and I actually know there is a better way, but I think maybe can SIMP even do this already?
Well, let's see.
Yes.
Okay.
So that's not very interesting.
Well, that's one way of knowing that it's in the database, or at least some components of it are.
We can also take cases of L. And then the first case is very clear, like that this is not equal. I'm wondering what is the tactic actually for this. So maybe let's look at some tactics to say something very obvious. So this is just the tactic documentation.
Yeah, so we need like a list of tactics, which I always struggle to find.
Yeah, yeah. That would be preferable.
And you want lean 4, not lean 3, which is what Google always gives you.
Yes, yeah. That's why I haven't found the list. I'm just trying to find something for the negative case. Okay, so structuring, that is not so interesting. Combinators aren't useful right now. Rewrite isn't useful. Okay, we've already done sump. Maybe that isn't that useful either. Okay, but we'll use this later. We'll look at this. Okay, damn. Is it
What are you looking for? Like
yeah, something like contradiction or
yeah,
terminate that we have in. I feel like it is.
There is a contradiction tactic.
There is. Okay.
Yes, just called
Okay.
contradiction.
It just failed. Okay, so that's okay, but that's good. We might.
I think there'd be.
I also wonder, right, if there is. We should be able to unfold, right? Like, but is it called? What is this called? NE? Oh wow, this is nice. Look at that. We can't do unfolding either. Like, if we can get to introing it, right? You understand what I'm saying? Like, if we can unfold not equal, then it can become a hypothesis, and then we should be able to use contradiction.
Yes.
I think. But I can never remember how to unfold things that are notation.
So NE is the, what does the at mean?
I think, oh, did that work?
Now it's just renamed, it's just changed it.
No, okay, sorry. So I think it's the at is that there for the type inference, right? So if you don't want to use type inference, you can explicitly say this is a list of alpha. The first parameter is a list of alpha, and the second parameter is a list, and the third parameter is a list. But really, when you say not equal, you don't want to pass in.
Yes.
The first parameter. So
got it.
Yeah.
So are you meant to type simp and then in brackets the name of the function you want to unfold?
Yeah, but simp is too powerful.
Oh, it's too powerful. Yeah, I'm just looking in the documentation. This unfolds. Yeah, wish there was a list of tactics.
I think I feel like I've definitely used unfold in one of these other files.
Yeah, I can't find it.
There we go. Here's an unfold.
Okay.
So it exists. But yeah, you need the function name. And in this case, we have any, but
Oh, and
How about unfold not? Or what is not?
slash something. I did backslash neg, I think.
I think it's just not.
Oh, not. You can also, okay.
But again,
Failed. Equation lemmas. Oh, hi, Stefano. Did not see you.
oh, hi.
You were pretty busy. I didn't want to interrupt.
No.
I was listening the last 5 minutes.
Oh, sorry.
No, I was searching on my side also to try to understand what you're looking for.
Yeah, we just like sump works here, right? We can prove the whole thing with sump, but we just kind of want something. We want to go very slowly, so we're just trying to see like, can we just unfold not and do like a contradiction type proof? Because obviously this is false.
Yeah,
And can we just
but
prove it?
not shouldn't be for one element or for using for proposition in logic, while unfold is like recursive.
Sorry, say again.
No, it's a but I don't know, because not usually used for logic for proposition. No, so it's like you negate something.
Yes.
And so is one element, and unfold instead should be then returning you a list. I'm not sure what you're trying to do there.
Okay, so what I'm trying to do, right, is I know that not equal is just A equals B implies false.
Okay.
So I want to unfold it to get that. And then I want to say, okay, now that I know A equals B implies false, put A equals B in the hypothesis, and then I can say contradiction, because it's impossible for an empty list to be equal to a list with one element.
So
I actually want to say unfold NE, which is not equal, but apparently I can't do this.
So can we print proof terms? So can you just use simp and then print the proof term to see what the proof term actually looks like? I can't remember how.
I think so. Yeah.
We mean, yeah.
That's a good idea. So here we go.
Oh, fun. Okay.
Yeah.
Right. So
Of
list.no confusion.
Yeah.
Conger arg not. So the fun is the intros, and then the of eq true.
Yeah.
He. List.no confusion. What is that?
So this is, yeah, here we go. What is no confusion is, well, we can maybe even go there. No, that takes us to list. Oh, or does it?
So there's no confusion. Is it that part of like decidable equality or something? Type class?
Oh,
I think it might be part of a type class.
yeah, that looks right. I don't know what.
If you go to like,
Wonder if I can.
protected def has decidable equality. So if you click decidable equality, decidable.
Why is this so hard? Okay, that's not very helpful. But I do think this is that this is okay. I'm using the hypothesis and I show that it is not equal. That's the no confusion part.
Mm-hmm.
And that's why I'm saying it's equal to false. And this thing. So basically at this point, right, it was already lifted to the hypothesis. So what does cong_argden do? I think this, yeah. I think this helps lift it or unfold it.
So this says, right, so this is the, what is it, Leibniz. We have two, A1 and A2 is equal. You apply F to both of them, they remain equal.
Yeah. So here they've applied not. Yeah, I don't know how useful this is.
Yeah.
in hindsight.
Maybe you can go, you can write the full proof term, or you can skip to the end. But you can't do an intermediate thing. Interestingly, in the standard library, I cheated and it just says equals fun.
Yeah.
Then the whole thing is inferred.
Yes. Yeah, exactly. If you
saying
go
like,
I copied
I assume that's what it means. It means like, well, I got a function here and you can figure out the rest.
I do think it requires some of these imports. I don't want to get into but, yeah. And here we do like using congruence arg. Oh, this might be just Kong from the little typer.
Yeah, I think it's Kong.
Yes. Yeah.
And then there's not Kong. Congru.
Yeah, but they're not using tactics very heavily. This is very much oh, here's a tactic. There we go. Finally. It's hard when you don't know the basics here.
Yes.
Stefano, do you know if there's a list of tactics somewhere for Lean 4?
No, that I no. I don't remember. I remember that at the workshop, again, we were using Lean 3. There was this very powerful and weird way to say that it was almost like natural language. You were like putting the mathematical theorem, and the Lean was able to look. Maybe you mean that, and but this was for with the mathlib, because there are literally thousands of tactics there,
Yeah.
and I don't know if it's working also for Lean 4. But an official list, I think, is impossible because of the nature of Lean at this moment is really so, changing. I don't want to say every minute, but at least every day. So the list will be quite easily outdated.
Yeah, but there are some basic tactics that will stay the same. For example, like sump and contradiction and things like this. I think we just need a basic list. Otherwise, we're kind of grasping here.
Yeah, I know what you mean.
Just trying to see if there's any. Just looking at the source code to see if it's like a
And that would be great.
list.
Can you just share the Visual Studio Code link for the share notebook?
Oh yeah, let me do that. Oh, sorry, I thought
No
I did
problem,
that.
no problem.
And
Yeah, you did, but
I pasted the wrong link. There we go.
Cheers. Thank you. And today I will try to log in with my
Yeah, 1 second. And that's going to be different. Yes. Okay, yeah, I think we're screwed. So,
I hope you don't mind me pasting this in the. There is something in the source code which lists lots of tactics.
okay, put it in the Twitch chat.
Yep.
Or in VS Code. Okay.
You search for tactics.lean, and this file has many tactics with some documentation.
Okay, yeah, here we go. Yeah, this is good.
So it's like contradiction closes the main goal if its hypotheses are trivially contradictory. So it gives some examples as well of stuff that should work. So I think, yeah, what you're saying is correct. Like if you had the not in the hypothesis.
Oh, I see. Okay, no, this is not what I was looking for, but
yes, well, it explains that that's why it's not the right tactic.
Yeah, but this is very helpful, very helpful. But yeah, I think we found the file we want.
Yes.
Thank you.
Excuse me.
This is amazing. Yes. Okay. Ooh, what is this?
With unfolding all, yes.
Wonder if it's necessary. Say with or. Okay. Okay. Let's see how this one works. Hey, that doesn't do anything. It did unfold.
Ah, excellent.
I need another tactic here, so it doesn't just, yeah, it's like a bit of weird.
It's like the no-op tactic.
Yeah.
I think you should put that, the contradiction.
Oh, yeah, no, we saw contradiction is not
Is not working, okay.
not what we need. I was wrong about that. But where is with, like, here's the syntax for it,
Yes.
but I don't think we see the actual tactic. It's
No. So syntax, tactic sec. Okay.
It's the tactic sequence.
Yes. So that's what
you need
comes.
to provide another.
Where has it been defined? So is it, maybe this is like in Coq, you have syntax, whatever it is, notation, and then the implementation comes somewhere else.
Exactly. Yeah, this is exactly what it is.
But
and I think that's what the macro is the actual tactic.
right.
And syntax is just the syntax for the tactic.
And I'm not sure, but I think some of the tactics may be implemented in the C++ or something.
Probably. Whatever they use in the backend here.
Mm.
Hello.
Hello.
Oh, hi.
Hi, Jan.
Hi.
How are you?
Hey,
Doing good. I had a family gathering.
Oh, wow. Cool.
I couldn't come earlier.
No. Shouldn't.
Yeah. So how is it going?
We're struggling, like,
Okay.
to put it very mildly.
politely,
Yeah. Not that I've been polite before, but like,
we're stuck.
yes, we're stuck. So, okay. So we're trying to prove this very simple thing. And you can just do it with sump, right? And it's proven. But that's no fun, right?
Yeah.
Well, not that we're having fun now, but we want to see how we can prove this in a more step-by-step way,
Right.
but still using tactics. And so one thing I want to do is so we have this case where some list with an element is not equal to the empty list, and I want to unfold the not equal, move it to the hypothesis.
So how is the not equal defined?
Yeah,
it's defined as okay.
Yeah.
I see.
Yeah. So it's this.
Mm-hmm.
But yeah, I don't know how to unfold it. So we're looking through this list of tactics over here to try to see if we can find something. But it's also quite a useful reference for a lot of tactics. So here's unfold, for example, but it doesn't work for what I want.
So by unfold, what exactly do you mean?
So I just want this definition of not equal to unfold. So I want this to become this.
Okay.
That's all. But I can't do unfold in E. That's not a thing. So.
But so if you try to introduce a new parameter, does it accept it?
I don't understand.
So if you intro,
Yeah.
does that work?
Oh, intro.
Yes.
Oh, yeah. We just need to give it a name.
Thank you, Jan.
Okay. Nice.
Still, I'd still like to be able to unfold stuff.
Yes. And we can unfold functions. We can't unfold notation at the moment. That's the one thing that's like not. But you know, that's something. This is a thing. And now like there should be a tactic that just goes, this is obviously false.
Yeah.
So let's, I don't think, oh, we can try contradict. Oh, it is contradiction. Okay.
Yeah.
Okay. Sorry, Stefano. I was doubly wrong. I was wrong about contradiction before, and then wrong again. And I guess there's two wrongs.
So this means that you were right.
Yes, I'm right in this case.
If
Yes.
you're a classical logician.
Classical logician. Get off the
I don't know if it's a
without.
compliment.
And in this case as well. Like, even though this was not classical logic, in this case, yeah. Because this is exactly what I wanted to do. And I was like, we should be able to use contradiction. And then we read about contradiction. We're like, oh, okay, actually, no, I was wrong. And then, and then Stefano proposed we do this. And I told Stefano, no, actually, you know, we read, this is not how it works. Wrong again. So,
Yeah, well, I wasn't sure. So I was just trying to.
yeah, no, well.
No, it's good to be wrong. Well, I hope so anyway.
Yeah. So this should be the same, right? Intro and no. Yes.
So it's already there in the right form.
Yeah. Okay. And
Yes.
technically, so maybe actually it's even right.
Mm.
We don't need a. Yeah. And then we can look at this proof. Much shorter than the previous one. Oh, before we add some to this, and sorry.
Yeah.
And then we got this, and we were, oh, that's not very readable. But yeah, we found a simpler proof, so we're good for something. Here we go.
And just to see what if you just put fun there? Does it actually work without the magic? No. Fun dot. I think it was just
Oh yeah.
And what does the proof term look like?
What is fun dot?
It just, well, I'm not sure, but it's
Okay.
the function introduces a function, but then it infers the rest of the arguments to this construction. I don't know. This is the definition in the standard library for Lean.
Yes. Yeah.
But what does the
when we looked up this proof before in the standard library, because
Yeah.
So
it could come from some magic somewhere else, or it could be like a legitimate thing you can do in Lean 4, but I don't know.
Yeah, it's not very clear, and it's not a tactic. This is because there's no by.
No, it's definitely a term.
So I think it is just inference.
Yeah,
which is pretty amazing.
But did it work in your? No.
Yes.
What did the proof term look like?
Oh no, I guess it didn't work.
No, it didn't work.
Yeah. And yeah, I'm not doing anything.
No. That's as far as we want to look into it. I just wondered if it was actually legitimate, like vanilla Lean 4.
Yeah, no, I think something else.
Maybe it is a tactic. Maybe it is. I don't know.
So
but it's definitely not a tactic. But
we did it.
I'm curious to prove it without tactics. Can we try? It should be fairly simple.
Okay.
Yeah.
So instead of the by, you introduce a lambda. I don't remember the syntax.
Yeah, so it's fun, isn't it?
Yeah, I think it's fun.
And then,
H.
okay.
Yeah.
And then match H with, and then end. You have no cases. It doesn't know that H is a contradiction. I see.
Yeah. I think if you go here now, we're at this place.
Can you have an empty match? Because here you don't know. Right. No.
Yeah.
Yeah.
Well, we can quickly check when this is. Oh yeah. So they use this list no confusion. So we
But
should
we
be
don't
able
know where exactly that comes from. It's some type class, but what type class we don't know.
So that should work. But
Oh, so it's no confusion. They claim in this random chat is something to do with injectivity of constructors.
Okay.
With a confusing name, which is ironic.
yes,
Well, maybe it's not so confusing when you think about it. But
it definitely confuses.
I never want to name anything with the word confusion in it.
Yeah.
It seems like a bad idea.
Yeah.
Okay.
So yeah, I'm not sure how helpful this is, but yeah, that's.
So injectivity of the constructor. Okay.
It uses some decidable type class to figure it out. That this is false, I guess. Okay. Let's do some more and try to do them without cheat codes this time. So how about this one that we have in Coq?
Yeah.
So let's just rewrite this. How can I actually, is that valid syntax? It was actually very, it was valid syntax.
Oh.
Wow. Well, that is very handy. You know, we're just gonna conventionalize it here, but that is very handy. Oh, no dot. Yeah. And then okay. Oh no. Okay. I was wrong. So close.
But doesn't it have implicits? I'm confused.
Oh, maybe it's this. No, that was correct.
Where is the?
What did I copy wrong?
But it's complaining about something which doesn't exist.
Oh, maybe. Yeah, it does have implicits. I shouldn't even do that. There is no 32. So.
Oh, maybe I've typed something. I don't know. No, I haven't. That's odd. Okay.
That is very odd. So let's just restart this. What?
It's like those messages are stale.
No, they're not. They're updating.
Oh, they are. It's not. I haven't got some phantom stuff that I'm typing.
No. Okay, I'm gonna retype it.
Maybe you could detect that it was pasted from a Coq file.
Yeah.
Sabotaging it.
Yeah, what is this? Okay, I'm gonna do this. I'm gonna do this.
Oh my god.
What am I doing? Okay, like,
oh, maybe just put sorry or something.
okay, yeah, good idea. Ah, there we go. Okay, list. And
So I just tried to ask ChatGPT to prove this theorem in Lean. It gives some answer actually. Which...
yeah. Fine, I'll allow it. What does it say?
Well, I'm not sure if it's LeanProver though.
Oh yeah.
You can look at it in WhatsApp. But I'm sure there is a simpler proof.
Okay,
But it's quite impressive that it.
Can you put it in the Twitch chat or join the VS Code and paste it there? I just sent the link to the Zoom.
Or paste it in the Zoom and I can relay it.
How can I paste it in Zoom?
Oh, there's a chat which is almost impossible to find. It's in the bar.
I found the chat.
Yeah.
Send file. Okay.
Yeah. So okay, this was just.
So what was the problem?
Once you typed sorry, the problem went away.
Maybe that's all it wanted. It's intercal.
Oh, there it is. It's still there, but but at least we can. Oh. Yeah, here we go. Here we go. Okay, just look here. It's all sane. We'll just say up here. Okay, so I think we can do like induction on list.
Cases should be sufficient.
Yeah, that's right. And then this should be simple. Well, can we do simp length only? Oh, unfold length. Yeah, okay, that does it. Or even we don't even need to do that. We can just do intro and riffle. Yeah, because empty list is equal to empty list. And then in this case, okay, yeah, so we need to prove this contradiction over here, right?
Yeah.
So unfold length and use contradiction, I guess. Well, or contradiction immediately.
Or that.
Oh, some leading alphas.
Oh, okay. Okay, maybe before. There we go. Yeah. We did unfold, so that's good. And then we can do intro H, yeah. And then see contradiction, yeah. Was it possible to do contradiction before? No. And if we do intro H and then contradiction. Yeah, it could figure it out
Mhm.
without even unfolding length. So that's good. And then this intro is probably not needed. Oh, it is. Okay. What did GPT, what did the AI say?
So it first proved that length of nil was 0. And then did cases. Well, this looks like lean 3,
Yeah.
Okay.
which is still impressive.
Yeah, can you paste it into the
No, because it's an image.
okay. Okay.
Okay, let me paste the text.
Oh,
I
right.
don't
Yeah.
know if it's gonna be formatted properly or not. Well,
So truncated.
so I added lean 4 to the question, and now it says it's not possible to prove the statement because lean 4 is a programming language and does not have built-in support for theorem proving or logic.
Okay.
That's a hot take, isn't it, on the state of lean 4?
I think it doesn't have enough data about Lean4 yet.
It knows it's a programming language, though.
So it just lied. So it's just like, hey, I don't know, but I'm not gonna say that. Like,
yeah.
let me just lie and see. Like, okay, well, I guess that works for most people in life. So, all right, let's try another one.
Associativity could be nice. Of concatenation, I mean.
Yeah, okay. Let's work up to that one. Let's work like, yeah. Yeah, how about this one? This works up to that. Okay. Let's see. So this just says if I have two lists, each has at least one element, then their first elements are equal and the rest of the list are equal. But yeah, like if we can get to associativity of concatenation, that would be great. Just yeah, one step at a time. I think this is a thing.
Oh, nice.
Yeah. Okay. Yeah. I just remembered that from the readings, so that I did this morning. But yeah, it just splits up the if and only if, so we can prove it both ways, one at a time. Well, I guess now intro.
Yeah.
I really don't like this red squiggle here. It really irritates me, but
Yeah.
it's actually nothing.
Looks like a syntax error. It's trying to tell you there's an error on that line, but it's not. Just incomplete.
Yeah, but there's not. Yeah.
Yeah.
Well, now split. Right.
Yes.
No, that's not a thing. Apply and intro. Yeah.
Yes.
Okay. So,
So you can do that Kong thing with the head, maybe.
oh, wow, that would be
But I
good.
don't know. Did you want to apply head to both sides of the equality?
Yeah, that would be amazing.
But
We look through this list.
was it congru?
Here's even a
Congruence. So can you do congru?
yeah, this is the only Kong. But you know, let's see. No.
No, but maybe you can. What was it?
How did we do this in
Not a tactic, but
Coq? Inversion.
seems.
Yeah, we kind of want the opposite of. Yeah, inversion was such a powerful tactic.
Yeah.
Injection. Yeah. I think injections. Yeah, there we go.
Ah.
Yeah. So it destructs the things. So if you have two things that are equal, then and they're both constructed with the same constructor, which they are because they're equal, then you can apply injections, and then it says the things inside have to be equal. So in this case, the two sides of the list, the two sides of the cons, the two parameters to the cons, and then
Right.
so in this case now it's assumption, right? And then this should be the same. I'm not even looking. Am I? Oh, and I should have looked. Why?
So injections didn't work here? Or did?
It
Must have
did.
the red squiggle, doesn't
Oh, I spelled assumption wrong. That makes much more sense. Okay, and then
great.
this side will be slightly different. Can we do apply and intro in H? No. Destruct H? No. Cases H? Yeah? Did that do a thing?
Yes.
Sort of, but not, you know. Yeah, I guess that works, but I feel like it's the wrong tactic name for this. But now What? Did that do it? Yeah.
Okay.
Okay. So what? Okay. Okay. So we did cases, which is not the right tactic name, not really what we want to do, but you know, it did the job. And then I said conger
So this would,
congruence.
right. So we figured out it needed cons,
Yes.
maybe.
I wonder if I do this before cases. Yes, nice.
What? It's squiggling. Oh, because
No, it's not done, but
oh,
this is makes more sense, right?
yes.
Whoa, whoa, okay, whoa, someone's editing. Okay, so it yeah, it applied. It's exactly the opposite of injections, basically. It does injections on the goal, and then you still have to prove it. But now it's kind of obvious after you. Oh, there has to be a better name for cases on an and. Like split H. No. Is there a? I need a conversion thingy.
Yeah.
No, that was close. That was close. So. Oh. No. Okay, can't figure it out.
Unhygienic.
Whoa, what?
Something called unhygienic. Hygiene disabled. Name hygiene disabled. Okay. Oh, if you want things to work like cock, you can.
Yes.
You can.
No, that's okay. That's okay. We can.
Yeah. Yeah, that's a. I thought that was a good change, not to have the.
Yes. Maybe it's still injection. Like. No. No. Cases is such a bad name for this case. Oh, save. That's good. Okay.
Remember.
Yeah, I hope that's remember.
Yeah.
Let's remember that save is remember. Actually, you know what? They should have an example of this, given all the ands and ors they do here.
Right. But I think they just apply the terms, apply the functions.
Yeah, but did they ever apply it? They don't ever apply it in the hypothesis, do they? Oh, that's impressive. They got away without doing that. I don't know how to do that. So this is all forward reasoning. This is what we're saying.
Yeah.
And no backwards reasoning. That is impressive. Yeah, I'm definitely not this smart. Here we. So you're at introed, right? And then it said, okay, cases on the right side of the hypothesis. So we can get Q and R. But this was for an OR. Then on the other side, we went, okay, cases on H. Let's do H and Q. And then we show something. Oh, we just go, it's the left side. So then in this case, you say H dot left, exact.
Huh.
Yeah, there we go.
Nice.
Yeah. Okay.
And what happens if you do cases?
It works, but it's just
Okay.
cases H, right? So what it does, it just creates these hypotheses without names.
I see.
So it's kind of, yeah, kind of ugly. I don't know. It might, but it works. It's just a weird thing to say. Let's take all the cases of an AND, where you would say, let's take all the cases of an OR. That makes sense.
Hmm.
If you think of cases as pattern matching, maybe it makes more sense.
Yeah. I think cases H with, I think you can do even a match. Yeah. And then you can say and dot intro. Oh yeah, this is one case, sorry. And then you can go HL. Can you do this? End. Do we do end on match?
Yes.
We have to say exact again. Okay, let's do it here, maybe. Doesn't like the end. Insufficient scopes. What? Okay, I don't know.
Yeah, never mind. But what I meant is if you think of cases conceptually as pattern matching, maybe it's not as ugly.
Yes. Yeah, that's true. Okay, want to try something a little harder while we work up to maybe something with a pen so we can get closer to like commutativity or associativity. What is easier than that?
I think associativity is quite easy already.
Oh, okay.
No?
Oh, we'll see. We'll see. Okay, let's do it. Let's do it.
Did we prove associativity of addition for the naturals? I don't remember.
Yeah.
Then this should be isomorphic to that.
I would be surprised, but you might be right. Okay, so we can even go check, right? Yeah, so this was associativity for our lex function.
Mhm.
So we just went cases on A and then it was all reflection. So let's start. Cases on L. That's all.
But we will need induction for
Okay.
lists. Yeah.
Okay. I also think so. Yeah. Okay, so plus plus. I just want to. It is a paint. Okay, so okay, just double checking. Okay, so now.
So what is the associativity of?
You can do.
It doesn't show parentheses, but it should, right? Or not?
We should to do associativity. You shouldn't do before that the 0. So if we add an empty list to an element, we have a list with one element, and then recursively you do the associativity.
So like this associativity.
It's like with the sum.
Yeah. So, yeah. Now it's good because before, without the parentheses on the left hand side of the equal, you had the same expression in both sides.
Okay. Okay. Cool.
Right.
Yeah. Okay. No, it's better. Yeah. Sorry, Stefano, what were you saying?
I think it's better to write it. And try if my connection. I was saying that to do associativity, you do it like with the number, no? So you actually try to prove that L plus 0 is equal to 0 plus L, and then L, the next after, so as you guys, the number after 0, so S of 0 is 1, and then you do recursively like this by induction. You prove by induction.
But we're gonna do it on lists.
Yeah.
Yeah.
So if you add empty list.
So we're gonna do induction on L, the first list, right?
Yes.
Okay. Now this is our state.
Yeah. I don't
So we
remember how to do induction in Lean.
No, we are doing it. So
Okay.
like there's the induction tactic. So we just call that. And now we need to figure out, well, we basically want to unfold the paint again, but let's see.
I think you can use sim or raffle.
Yeah, but you know,
You don't like, yeah,
too easy.
yeah, okay.
You want to know what to do when
definitely
things are harder, when things, yeah.
Okay. Raffle's fine to use, I'll say. So
Yes.
But it would be nice to just see the two equal before.
But it's not fun to learn.
Yeah, but I think it's sometimes harder to get simpler than raffle. So
yeah.
Okay.
It's best to see what raffle actually is doing. It's
Once
like,
we finish the proof, we can. Yeah.
okay.
Yeah. It's hard to do it in the intermittent state. I actually don't know how to. Well, actually, maybe.
Will it
Maybe
print
this
something here? Interesting.
We are here.
Yeah, so it's doing the induction. List.rec is the induction on list.
And then let's just did a riffle. Like it's not
Yeah.
even calculating anything. So yeah. Cool, that worked. All right. Back to the proof. So now we know this. Just need to prove this. So I think we can say conger.
Yeah.
That might help. Does it help? I don't know if that really helped. Created these two cases where we have to prove the impossible and we have to prove the other impossible. Not so sure.
No.
And our hypotheses actually make sense. So I don't think this is gonna work. Oh man, why not?
But these should be congruence head T cons, right? Like, can you provide the argument explicitly in the for the tactic?
No, you can give it a number. So try giving it numbers like 1 or 2.
Okay.
No. I'm not exactly sure what the number means.
Yeah, we can go read here. So.
Well, then we can prove injectivity of cons X as a lemma, and then use it instead of conger.
But you could also apply. Couldn't you apply the congruence? So there's the congr arg, which is the function.
Yes.
With whatever with the f, so you can pass the f in.
Cons.
Yeah.
Or well, actually, yeah. Can we give this head and tail a name?
Yeah.
Maybe let's just see an example, hopefully.
Using R? No. Generalizing. With?
Yeah, I think it is using.
Okay. No, but it says using allows the user to specify the principle of induction that should be used.
Oh, yeah.
So it looks like it's the last example in the documentation.
Oh, here. Yes.
With.
Yeah. Okay, now cons, head, tail, and
Well, I think isn't it nil, or is it called 0? The first. Oh, sorry, you've not finished yet.
oh yeah, you're right. Yes, yes, yes. Okay, that's good. Then we were trying to apply Conger arg
Yeah.
cons head. Yes. Assumption.
Okay.
Wow.
There
Wow.
we go.
Wow. Wow, I never thought we would use Kong in real life. I really missed it. It's just like finally it's back. Yeah, so we had this, and then Conger arg turned it, which basically says, well, remove the head. So apply this function in reverse. So we had the two sides of the equality had cons head applied to them.
Yes.
So we can apply it in reverse, and then we get it without the head. And for some reason, these are unfolded, and not the plus plus. But now this and this is the same, and we can just apply assumption.
Mm-hmm.
Okay. So yeah, Jan, I was wrong. This was super easy.
Nice.
Except for magically knowing how to use Kong. That was good. That was good. Okay. Another one.
So reverse is harder to prove.
Oh, okay.
Maybe we may want to have that for later. I don't know.
Well, okay. Maybe let's see.
Yeah.
Yeah, so reverse of list equal list.
So do you know if Lean4 has function extensionality?
I saw this
I think you
I don't know.
import it.
Well, what is function extensionality again?
So here we could say reverse composed with reverse equals ID instead of introducing a list.
Oh, okay.
But you need function extensionality to prove that. So function extensionality is if the functions are pointwise equal, then the functions are equal.
Yes.
Yeah, but
Let's also we can print.
and try to Google it.
Yeah, so there's this. They're improving in Lean4 with the talks about the axioms. So if you just do check fun ext,
Okay.
then if it's in scope, because it's claims to be in the standard library. Yes. So they have some axioms about quotients. And then they prove function extensionality from that.
Okay, but they need some axioms that are not part of the language.
Yes, they need some axioms, yes.
Okay.
But I think the axioms are in the standard library. So this is a theorem that you can use, and it comes from it's been proved using some axioms.
I think it's like this is still valid intuitionistic logic, right? It just means you can't like compile some things if you use this.
Yes, you cannot run anything that uses funnext.
Sorry, say again. You can.
You cannot run.
Yeah, you can run it. Yeah,
Yeah.
but it's still valid. Intuitionistic logic. It's not classical logic yet. It's something, or is it something in the middle?
Well, I suppose it depends on your logic, doesn't it?
Yeah, so that's what
Intentional
I'm
and intentional.
Does this fall under intuitionistic logic, or is this a step further? Because it's not classical logic yet, right?
No, yes, I think you're right.
That's the only part I know. Okay, we don't know. That's fine.
I mean, I think for classical, for sure you have this, and for intuitionistic logic, you can have it or not.
Yes.
Oh, okay. Okay.
Yeah.
So there's not a new logic name for having it or not. It's kind of a.
Wasn't it like intentional?
Okay.
Yes.
Yeah.
Intentional logic or intentionalistic.
Yeah, like intentional logic with intentional or extensional equality. I
Yes.
think that's how you say it.
Okay, but so what do you want to do?
Well, prove this theorem as it is written by using this for next. Yeah.
Okay, that would be interesting.
So prove this theorem using phonics.
Yeah, I mean, you start the theorem by applying this axiom, and then it looks exactly as you had it before. That's my expectation.
Yes. Oh, sort of.
Yeah.
Yes. Well, okay.
Yeah, I mean, if we unfold composition, then it will look like before.
Let's see.
An ID.
Oh, that worked. Finally unfolded. This did something. Been waiting all day for unfold to be useful.
Can you unfold ID all at once as well?
Oh, yeah. Well, okay, let's just do it in 2 steps first and then see. Okay, yeah, it worked. Okay, now let's see. No. And maybe
that doesn't work.
no. Yeah, that worked. Just different syntax.
Just try all the syntaxes until
It worked.
Usually
right?
it's a list, isn't it? Usually it's a list, literal list. Strange.
There's still a tactic, no? Try all.
Yeah. Yeah.
A meta tactic.
Okay, so now we can start the proof, right?
Yeah.
Yeah. So induction X is, I expect. And this yeah, Raifel can figure that out. Okay. Oh no, okay, sorry. What's the problem? Ah, cons.
Right.
There. Uh,
What?
so yeah, so sump reverse does some work, right?
Mm-hmm.
But it calls the reverse auxiliary function. Let's see. Yeah, that does something.
I guess it's a tail recursive helper function that it uses internally.
Yes. I wonder if we also do unfold reverse. Yeah. Earlier.
Oh.
Can we print reverse to see how it looks like?
Reverse aux, maybe.
Yes, reverse.
Yeah.
Hmm.
Break on.
Yeah, great.
Where's a motive though? That's nice. We know about motives.
Yes.
Not very readable.
Oh, oh, what about this is risky, but hey, that looks more readable. So I just unfolded it.
Okay.
Yeah, much better than front. It unfolded the wrong one, but you know, at 2 maybe. Is there something here about unfold?
Well, it's got
Location. No, we're not going to learn anything about location, are we? Oh, we are.
empty. At.
Oh, that's the hypotheses. Everywhere. Ooh, with position.
Yeah, so that's just the code version of the docs.
Ah. Yeah, okay, so we don't get to pick. Okay, so we just unfold both. this is the one here. So it should go down this route. Oh, come on. Now, you know, I really want to force this here. Oh, not today. Oh, what was that? We had that. Other tactic. Sorry, just give me 1 second.
Simp only.
Yeah. Yeah, it was some only. Okay. Yeah, sometimes some only would do some stepping forward. It's like, because clearly in this match, right, we could just go the, oh, we can't. I haven't done this proof in so long. Did we ever do this proof? I feel like we did. Does it require 2 inductions?
I don't remember.
Okay, well, let's just go back for a second here. Well, okay, maybe here. Okay, maybe here, yeah. Yeah, so reverse orcs just keeps prefixing whatever is in its list to the front of the result list. And that way, the second argument is the result list, right? Which will be the reverse of the first list at the end. We've already started by adding the first element to the result list, x prime. well, not the, we're going to reverse that again. So we've just, yeah, added to the first result list, which will give us the reverse. And then when that's done, we would reverse it again. So we don't have a generalized x's in the hypothesis. Which might have been helpful.
Hmm.
Like, how do we get that first? We got it to move a little bit. But we wanted to move. Oh, it won't ever move over here. It will be the last thing that moves over there. Yeah, Jan was right again. This is really, really hard. When he says things are easy, they're very easy. When he says they're hard, they're very
Yeah.
Kind of oracle.
yeah. What is,
Also, maybe if you define reverse like in the more inefficient but easy to understand way, it will be easier to prove.
well, this is how I would actually define it. What is the easier way?
Without the recursive auxiliary function.
Okay. So we would have,
So you keep yeah. So that is reverse XS concatenated with singleton X.
doesn't like the end. Yeah, I just don't think the end is needed.
Oh,
I
interesting.
don't think it is needed.
Maybe I confused the end of
Or-
I saw it in the documentation, I'm sure, but maybe it was the end for something else. I don't know.
Oh, yeah, also when we print things out, look here.
Yeah, doesn't have it.
I also thought there was an end. It's not just you. Okay, we don't need to unfold it now. So, all right. So now we can do some reverse. Yeah. Okay, so it can't be this, but it doesn't know that. Oh, look at that. He didn't rename those.
Hmm.
So, yeah, it's gonna do, I don't know, can't remember what you call this. So now what? Yeah.
Let's see. Trying to. What do we have? Much.
We can rewrite x's prime to be reverse, but yeah. Well, no.
Hmm.
Is that something
So,
like
if we have, I think that we need a lemma like reverse A concat B.
okay? So what would the lemma be? Sorry.
So reverse of A concat B.
Yeah.
Sorry, A and B are two lists. Yeah.
Okay.
So this is equal to how does this distribute? Is it just reverse B plus plus reverse A? Is this correct? Yeah, right.
Yeah. I just need to spell it.
And when we have, is this true?
Yeah, that will at least I'm thinking as well.
Yeah.
I think so.
Okay, so then when we have this, can you go back to the goal we had?
Yeah. Okay. So let's see if we do. No. Yeah. Not what I wanted. But okay. So we're here.
So the idea. We don't have line numbers. Okay, so in the second match case.
Yeah. Yeah. Yeah, but it's not.
It's not. I mean, so we have like we can add reverse of the singleton is the same, right?
Yeah. Yeah.
No, but I'm not sure this my idea helps.
We'll see. We'll see. So we can. What? It didn't do anything.
Well, maybe we can just imagine it for now. So
Oh, I don't have any imagination. No. Yes. Okay. Sorry.
so the idea is that then we have reverse xs prime plus plus reverse of singleton x prime.
Yeah.
And then we can use the lemma to have reverse of singleton x prime concatenated with reverse xs prime, and then we can use the lemma, the induction hypothesis in xs prime. Maybe I can try to spell it.
No, I'm just thinking. So yeah, so okay, we have this, right?
Yeah, let's write it. Okay.
and then it becomes this,
Mhm.
and then this becomes
no, reverse X prime.
yeah, but I don't think that's what will happen.
No. Yes, that's correct. But then we can add. No, wait. What do we gain from this? Nothing.
Yeah, so
No, never
proofs
mind.
with lists
Never
are
mind.
proofs with lists are very annoying to do. This just proves the point that we
It
have
proves the point that you're trying to make. This is the
Yes.
goal of the.
that we need to have a big list tactic to do all these things for us. So like, which is the point of the effort we're starting here. So because these theorems are not like fun to prove, even though they're relatively simple. I really expect this rewrite to work. I like. But yeah, I think you're onto something where you're because we need to generalize a bit more. I was also thinking like maybe it's helpful to prove prove this. But yeah, I don't think so. I think it's more in the line you were going. But you can see if we can prove this one at least. How about that?
Right.
So induction on X's. If you're trying to say something, Jan, you are muted.
Sorry. I was saying maybe we can try to prove first a simplified version of this theorem,
Okay.
where ys is always a singleton.
This one.
No.
No, X is any list, but Y is a single.
Oh, okay. Okay, I see.
Yeah. So, well, you can have cons y reverse xs. We can forget about the reverse and the append. No, this is so. No. This is correct, but
Yeah.
after the equal sign. Yeah.
Okay.
Yeah. Exactly.
Cool. Okay. Syntax correct. Okay, now induction on X's.
Mhm.
Then let's just do this right again. So I'm pretty sure. Okay.
Let's see.
So I think if this moves a little forward, it might get to this. Oh,
Yay.
okay. Well, that's come on. That's not what I want.
No, let's not use simp.
I just wanted to move a little forward, you know. I think that did something. No, didn't do anything. Unfold. Oh, look at that. Oh, no, that's correct. So I just wanted to go here. Can't figure that out
Maybe
without going all the way. What about decent? I think, oh, yes.
oh.
Ah, no. No, it didn't do anything. Oh.
But let's see. Let's try to. Does this unfold help?
No. No. So this is where we were.
Right.
And then the unfold just does this. Doesn't actually step forward. And then some goes way too far.
Hmm. Okay, but
What about?
but by the definition of, we can apply the hypothesis, no? We can rewrite the hypothesis.
I did it. Here we go. I think. Did that do something? Okay, that did very little. So sorry, Jan. What were you saying? I'm sorry.
Can we try to apply the hypothesis, like rewrite it?
Which one?
The one that doesn't have a name.
Yeah.
Oh. Ah, yes. Why doesn't it have a name?
How can we give it a name?
Nice.
There we go. I did it. I just added an H after con, so Okay, so you want to apply this? Well, I don't think we can, right?
Yeah, because reverse prime, I mean, here it's not simplified, but reverse prime of x prime cons something else normalizes to reverse of x prime plus singleton y plus singleton x prime, and then we can provide the first part.
Okay.
It's yeah.
Okay. I think.
I cannot figure it out.
Yeah, it expects these, and then
What's it complaining about here?
maybe.
Yeah.
I cannot apply it.
No. Yeah. It cannot rewrite. At least.
But can we do it by hand?
Okay. I find that really hard to do rewrites by hand. But like using the.
But let's at least apply just the first step.
Okay, how?
So can you write what you have on the left hand side of the equal in the goal? In the goal.
Oh, in the goal. Yeah.
Yeah. So by definition, this is equal to reverse prime of xs prime plus y prime. Yeah, exactly. Plus singleton x prime.
Mm-hmm.
Right. Oh, so this is what you mean by hand. Sorry, I thought you meant like yeah, instead of using the tactic, there's like really hard ways to rewrite that.
Okay, no.
Yeah. Sorry.
What do we say? We say have to introduce this. Have.
Yeah.
And here we have xs prime plus y, well, reverse of this, which we have in the induction hypothesis.
So we can say have. Can we say this? I think we need an example. No, you give it a name and then you say how you prove it. So like have HR colon. So then this would be what we
Raffle.
had. And then we can say by. So yeah, we can try to prove this.
This should be by raffle. I mean, this is by definition.
Yeah, cool. Nice. Okay, we have that.
And then we can rewrite the induction hypothesis.
So rewrite the induction hypothesis in HR.
Yeah, on the right hand side we have reverse prime of.
Yes.
Yeah.
So try rewrite.
Oh, here.
Yes.
Okay.
Can you rewrite in HR?
Let's see. Rewrite H.
Yeah.
In HR.
Is it at?
I mean, we can rewrite HR in the goal and then rewrite the hypothesis in the goal. Maybe that's simpler.
No, this worked.
Yeah.
Okay.
Yeah, that worked. So we have. Okay, and this is, I see this is now here. These two are the same.
Yes.
Oh.
I should be able to rewrite that in the, just rewrite HR.
Oh, they're not in. Oh, here. These right sides are the same. Sorry. Left side. Sorry, I mean left. I always get confused. So we should be able to just say rewrite HR. Okay.
Yes.
And then we use Kong, I guess.
Yeah.
Well, Kong, what we did before, like the Kong arc.
Arcs
Yeah.
with
Oh,
Kong.
that.
Yeah.
That. Where was that? Oh, yeah, that. Yes.
Yeah.
Cons Y.
Why? Okay. Isn't this just raffle now? No. Okay. Not that lucky. No.
So we got reverse
So see now reverse needs to step a little. So
Yeah, this should be by raffle. Why is it not by raffle?
oh, here we go. Let's see. So this simplifies to that, right? This can be this or that, and then only we append the x prime. Yeah, that doesn't. But yeah, it's so close.
But
Obviously, simple can do this, right? Yeah. Oh no. But at least, oh, Sim finally did something useful. It didn't prove the goal. Oh wait, can we go back? I don't know if that was very useful.
Yeah, sorry, I have to leave now, but
Okay.
hope you figure it out.
Yeah. Thanks for coming.
All right, see you
Have a
next
good
time.
weekend.
see you, Paul.
We're so close, man. Sump again. Some can't even prove this. That's this is where we were.
Yeah. But okay, so if we look at the right hand side, by definition, like
Yeah.
I still don't see why this is not equal to raffle,
Yes.
because it's exactly our definition.
Yes. Maybe you can fold. No. There was something we were able to do in cock. It's like refold something back. Like in this case, I just want to unfold the second reverse. So we can say and this is like a trick to unfold, right?
Right. Yeah, let's try this.
And then what? How is this? Am I misunderstanding a paint? Oh, okay. Okay. We got one wrong. We got one wrong. There we go. But it was interesting that I could prove this by riff. That was helpful. Yeah, but if we can't prove this, then okay. So the cases X's, I guess.
No, I don't think. Wait, it couldn't prove it.
No,
Why not?
well, it doesn't really tell me. It's not equal, so
But why not?
well, that we have to figure out.
But it's okay. Maybe I'm not reading it properly, but I mean this is
This is why. Here we go. I forgot to quote here.
okay.
Yeah,
Yeah.
we probably don't even need that. Yeah.
Yeah. Okay. Now it makes sense.
Wow. I
Yeah.
really thought it was. Oh my, that's okay.
Makes sense. It's a big word, but okay.
Yeah.
Yes, I have to leave too. I will check the recording because
No, we're gonna end soon, so yeah, don't worry. But yeah,
Okay.
thanks for coming.
oh, thank you. Bye.
See you.
Bye.
Yeah, so we just spelled this wrong.
Yeah. Okay.
Or I
No.
did, and yeah. But yeah, I think that might be good enough for today.
Yeah, it was great. We can use this lemma to prove reverse reverse later, hopefully.
Yes. Yeah, so I'll try to put up what we've done on the GitHub repo, and then we can continue more next year
Okay.
after all the holidays.
Yeah.
Yeah, but yeah, thanks for coming, and yeah, thanks to anyone who's still watching.
All right. See you.
Yes.
Bye.
Bye.